Okay, everyone awake now? We got fresh air. We should do this every morning, right? Before we start class. Okay. So I believe before the alarm went off, I asked any questions about the logistics. Any questions arise while we were standing outside? No? Okay. All right. So I've had a few students ask me, they say, okay, they like this class. I don't know if it applies to everyone, but they like this class. They say, all right, what should I take for Tech Elects? And what are some recommendations? So I'll post this to Carmen as well, so you don't have to like scribble down these notes. But I just wanted to quickly go through some options if this is of interest to you. So the class is probably most related to this class is Design and Control of Mechatronic Systems. This is being offered fall 2019. So that would be the most logical next in the progression of classes if you were to take something that's similar to this. Okay, so for those of you playing Tech Elects, you may want to consider that. There are some other classes that you may not necessarily think of that are outside this department that you may be interested in as well. So control systems is kind of a hybrid between mechanical engineering and electrical engineering. So a lot of the control systems classes are out of the ECE department, and you should be able to get Tech Elect credit for these. So everything we're doing right now is in continuous time, and we're not really talking about what is happening in, say, a computer or microcontroller in this class at all. So if you wanted to learn some of the real basics of that, it'd be Intro to Digital Signal Processing. That's offered every single term. So that's offered both in the fall and the spring, if you're interested in that. And then there's another class out of ECE that's very similar to mechatronics, but it is a different alternative. This is called State-Space Control Systems. So this is a different way of looking at systems analysis. So we look at everything in the frequency domain in this class. We actually be looking at everything in the time domain. But this helps you start to understand how do you control multiple input, multiple output systems. And then another class that is not on the books yet. So you won't actually see this because at both the EC and ME level, there's been some changes in the way this is offered. So every year previous this year, there's been an electrical engineering robotics course, and there's been a mechanical engineering robotics course. And we've been teaching exactly the same class, but doubling our efforts. So we're now merging those two classes together. And so this will be on there eventually is ECE/MECHENG 5463, Introduction to Robotics, if this is of interest to you. So this is looking at more of robotic mechanisms and how you control, and not necessarily control, but the dynamics of robotic mechanisms. The spring, digital control engineering, which is kind of a mixture of the DSP class at EC and mechatronics. Intro to signal processing is being taught again, and then this last one, I'll put this with a very stark warning. This is, for those who go into graduate school studying controls, this is often recognized as the most difficult class you would take in that whole series, so in the whole PhD. So this is really only if you really think you're going to go to grad school and study controls in grad school, you want to get a jump on this, and you don't care what your GPA looks like. Which last semester you may not care, but this is a serious class. This almost killed me in graduate school. So anyhow, you've been warned, I guess, if you want to take that class. So any questions about that? I'll post this on Carmen. Okay. Okay. So we finished up Monday's class talking about PID control. We got into what does the derivative term do, what does the integral term do, what happens when we mix these all together, and then that's kind of where we ended. And now I wanted to show a demonstration of this actually in work. So what we have here, we have a few different things here from just of a plant level. We went through the whole discussion of proportional derivative, proportional integral, PID control, talking about a mass spring damper system that was linear. So just to kind of doodle to the side here, that was this system. And so then we can force this mass, right? And we can write almost identical equations. The variables we use have different names. They look different, but it's essentially exactly the same equation for a rotary system. right? So we can have a rotary system that has a rotary inertia with therefore an inertia value J. It has a torque, which we can apply to it, and it has damping associated with it, and then it has a spring constituted. So that's exactly what we have here. So you see probably two rotary inertias. One I have fixed. I put these clamps here and just kind of rig this up so it doesn't move. And then you may notice that there's this rubber band here, which then goes to this pulley, and then you can see then this has this has a belt that then connects to this inertia. So this is what we're trying to control, and so therefore it's spring loaded, right, via this rubber band. So if I were to twist this, and let it goes back to its neutral position, and you also notice that it eventually stops oscillating back and forth. That's because it has bearings, and those have damping associated with them. Right? So this looks, schematically looks a lot like what we have here. We have some sort of inertia, spring, and also damping. What you can't see here is, well, you can see the motor. So here's what provides torque to the system. This is a DC brushless motor that's on the system. And then on the back side, there's another pulley and a belt that then connects it. So torque transmission from the motor, torque from the motor, then transmitted to this belt into this inertia that we're then trying to control position. Right? So this is kind of like a dummy system. This doesn't do anything, right? But this is representative of, fairly representative of things you can see in industry, right? In terms of robotic systems that have springs associated with them. We could always just pull the spring off, and now it looks more like a robot where it's free to rotate. It doesn't have a neutral position, but this is fairly representative of systems you may see in industry. So this thing's actually called a control systems trainer system, what it's called. Industrial emulators for training, in terms of designing PID controllers and other types of control systems. Right, so it's just a simple demonstration tool. Put that back on. Okay, so this is what we call the plant, right? Control systems. This is what we're trying to control. And our task here is we want to control the angle of this disc here to be at a certain angle, right? So if you can imagine this to be connected to something that moves an arm, we want to then position the arm somewhere to, like, say, pick up something that's on the line, right? So just kind of random task, not random, but purposeful task if you have some sort of industrial system. So the notes give what we have identified to be the different parameters for this. This is not all that important to this discussion. But if you wanted to go and simulate this yourself, this would be the parameters that define the system. And this is a control system. So if we want to look at what the other elements of this are, okay, so we have a feedback control system looped around here. So what we have in the system, I'll draw these elements first. Okay, so we have the reference signal, which is where we want this disk to be, and the controller, and it all lives inside this computer. So this is a like 7-year-old just laptop computer here. So we're not going to go into the details of what's going on here. This is not too important, but this is actually Simulink-based real-time software. So this is not how all industrial control systems are built. But this is, again, going along with the ideas of something that's like simple educational tool to build. This is very visual. And so you'll see a few things here that represent what we have in this image over here. I'm going to continue back and forth with my HDMI cable here, but we have a reference signal, right? And this is just going to be a pulse type signal. So you can actually see the form of this. We're just going to go from one level to the next, back to that initial level. We have negative feedback, plus minus, and then we have a PID controller here. And then there's some other things in here which aren't too important in discussion, some things in terms of data logging. This is a safety system. We'll show how this works in a little bit, but basically if we dump too much energy into our amplifier, which we'll talk about in a second, this thing will kick it out and kill it. So we don't fry a motor here. For our room, sure as everyone would like to see that, but we're not going to do it today. But this is basically the software that will be built inside of a computer in here. So other elements of what's going on here. Okay, so coming from the controller, in this system we have a D to A converter. Okay, so this wire here is actually just my USB cable. Right? This is connecting my computer here. So when you say a wire here, it's actually, in this case, quite literal. This is actually a cable that's sending information from my computer into this board right here, which does D to A conversion. So it takes whatever the computer says the analog output should be, and then it creates at this pin here that voltage. So if we were to take an oscilloscope, we could go and directly measure the voltage at this pin, and it should match what we've commanded it to do. Right? So this is a very physical thing. So this is the D to A converter is actually the transition from this virtual world to the physical world, where now we have something in terms of like the charge of electrons in this cable that's actually represented. That could be measured if we want. So then this travels along this wire here, and this is a voltage potential. And then this goes to an amplifier. So this would be in volts. The amplifier is this big white box you see here. Okay. So inside here, there would be basically a system that converts this voltage into something that actually has power behind it. So any data acquisition system, analog digital converter, digital analog converter, has voltage but really no current behind it. So they have all essentially open loops or open circuits in them to measure voltages but no power. So you could actually I could stick this on my tongue and I wouldn't feel anything, right? There's no power behind it. So we use an amplifier to actually put current behind it, and so voltage times current then becomes power, right? Okay, so what's coming out of here could never power this motor. We amplify the signal, we use an amplifier. That then travels along this line right here, and then this goes to my motor. So the next step along this would be current, I. This is my rotational system. All right, and I would call this entire assembly here my plant. Any questions about the idea that there's 4 loops so far and the hardware that's up here? Yes. So the short answer is there's nowhere else for it to go in terms of the standard system. But that is, we're talking about things that are physical that we're trying to control. All right, so this is actually physical. This is doing an operation. Right, so it's taking voltage and it's converting it into current, which then goes into the system. So if we look at what's coming out of my controller, it's a voltage command. Right, and so then controller has a transform from air signal, which is going to be in radians, to volts, and the plant takes volts back into radians because that's the output of my system. Right, so it's all lumped together because that's the physical things we're trying to control. Yeah.
Should the D to A also be current then?
That's where it gets kind of fuzzy. And that's where it doesn't, also gets to the point where it's starting to not matter too much, because D to A converters are really accurate and really good. So if you tell it to command 5 volts, it's going to be within the resolution of the D to A converter, which is, I think this one's 16 bits. It's going to be within millivolts of 16, or whatever I said, 6 volts, whatever. So it essentially has no dynamics associated with it because they're so accurate now, and they're really cheap now. All right, so then what comes out of my system is its position of this disk, theta, and then this is just kind of a phenomenon or some sort of, it just happens, right? And then for our system actually to identify what that position is, we need to have a sensor. So who here has heard of encoders before or know what they do? A few people. Have you talked about encoders in measurements class at all yet? You have not. Okay. So you've talked about potentiometers in measurements class? Some, or maybe freshman engineering? Okay, so this is potentiometers, encoders. These are all tools to measure the rotational position of something. Right. Okay, so an encoder is... Okay, so this system has 2 encoders. We only care about the one attached to the disk that we care about. So this is actually directly attached to the motor shaft of this disk. And so this is reading the angular position of this motor. It's fed through here. So following this block diagram along, the encoder senses the angular position. It then goes to an analog to digital converter. Okay, so it actually is traveling along this line right here to these analog to digital converters on my board. So I'm showing the D to A and A to D as 2 different blocks, but pretty much any modern system you buy is going to have both A to Ds and D to As on them as well. So these actually are on the same piece of hardware. And then this is sent back through the same USB cable into my computer to then complete the loop. Okay. All right, so that is kind of the assemblage of hardware you would need to buy and put together and get all working together to pull off this task. So since just only a handful of you have seen encoders, I just want to quickly talk about what an encoder is because I think they're interesting. They're kind of like the most basic positioning system you can imagine, but they're very, very effective. So if I were to, say, break open this encoder element here, which is just a plastic case, you can't see what's going on in there right now. But if I were to break it open for you, what you would see is you would see a disk, and then if you were to zoom really, really far in on that disk with a microscope, you really wouldn't be able to see it too well with your eyes. You would see then a strip, and the strip has depending on the encoder, either has little gaps in it or it has light and dark markings on it. Okay, so this is me zooming in. So this is a circular system, but I've zoomed so far and it looks flat, right? Just like the Earth, unless you are, like Kyrie Irving and think the Earth is flat. But this, you look at it, you see light and dark marks, or you would see gaps or no gaps. And then what you have here is you have an LED that illuminates the system. So this is my LED. And then you have a CCD, which then looks at, in this case, if we're looking at illuminating, this is a dark or a light mark, we're looking at what's reflected back, right? And so it's saying, all right, shine a light and look at what's reflected back, and then you can determine whether or not that area that you're currently looking at is light or dark, right? So this part is fixed. This doesn't move, and then this strip moves as you rotate this disk. And so if you have just one of these, and say your signal goes from dark to light, you don't know if you've moved left or right? All you know is that you're no longer on the dark spot, you're now on the light spot, right? So then they use 2 of them. So you have channel A, and then you have channel B. Channels A and B are 90 degrees, is it 90? Yeah, 90 degrees out of phase with each other. So if this one's looking at centered on this dark spot, the next one would be just kind of at the cusp of where it goes from light or dark to light. Okay, so as, say we rotate this disk at constant velocity, channel A would look like this. And channel B would look like the same, but it'd be 90 degrees out of phase. Okay, so now if you say, the high level is light and the low level is dark, we can determine now that we went from a 1 to a 0, we can now determine what direction we went by looking at channel B and understanding, okay, when we went from a 1 to 0, were we at a 1 with B? That means we went in one direction, or were we at a 0 with B? That means we went in the other direction, right? So it's a pretty simple tool. They're fairly cheap. They cost in the order of 50 bucks. They're not too expensive. More expensive than a potentiometer, but they're pretty effective. And so these lines here, I said, okay, you need a microscope. For a really good one, you have to have these are basically somewhere around over 1,000 of these markings per revolution. Right? So they're pretty precise tools. Okay. All right. Any questions on kind of the setup we have in front of us here? And after class, you can come down and look at it too. Turn it around, whatever you want to do. Okay, so what are we going to show here? So this demonstration okay, so this is what we're going to see. We're going to run this in a second. But what you're going to be looking for in every single run here, yellow line is going to be the reference signal. So we're saying reference signal is saying that at, I think this is like half second, the reference signal is going to go from 0 radians, that means the position it's sitting in right now at rest, all the way up to 1.5 radians, which is about pi over 2, right? Around a 90 degree return, not exactly 90 degrees. The magenta line is the actual measured position based off of the sensor, the encoder of the system. And then the blue line is going to be the input to the system. This is the voltage set by my digital to analog converter, which goes to the amp, which gets converted to current. Okay, so this is yellow reference, magenta output, and then cyan, blue line is going to be the input. So that's what you're looking at in every single one. And then we'll just go through a set of different conditions and take a look at what the response is and see if that matches our intuition. Okay, so the very first thing we're going to do is we're going to look at type 1. This has a proportional gain of 1, derivative gain, integral gain of 0, derivative gain of 0. For each of these, we're going to look at what's the peak time. That's a little bit easier to pick off than the rise time on a system. We're going to look at the overshoot percentage, and then we're also going to look at what C final is. For each of these, to see if this follows kind of the general rules that we talked about in class and whether or not this is in agreement with that. So the other thing I forgot to mention is that we have this GUI set up. Okay. So the GUI, this is just pretty simple. It just allows us to, so GUI, in case you haven't heard that, that means graphical user interface. Doesn't mean like, you know, you step on gum or anything. All right? So graphical user interface. And so we can set the proportional, integral, and derivative gain for this and then look at the different responses for the system. Okay, so we're going to do this first test. We're going to look at a proportional gain of 1. And then, all right, so I'm going to press play in a second, but it depends if you want to look at the screen, look at the scopes, or you can look at this thing actually moving. But I'm just going to press play here and you'll see it run. So that was very exciting, right? It moved. I'll plot this using this tool right here, because this automatically pulls off some information for me. So what we're seeing here on this plot is the recorded data. So when I ran that test, it actually recorded the data automatically, then we can plot this. And so we can look at, here was our reference, here was C final, and we see with a really weak proportional gain, we get pretty poor performance, right? This doesn't do very well, right? So we have a C final which gets only like a third or not even a third of the way to where it should be. Overshoot on the order of 30%, peak time 0.172, right? So we'll kind of log this and make our observations from here. So peak time 0.172. Overshoot, when I say 30%, 30.6%. And C final was around 0.42, right? 0.42. Okay, so pretty unimpressive response to this. We can then double the proportional gain. Run it again. Okay, so similar response. You may have noticed that it goes up a little bit higher. All right, and we run this again, and we see a few things that are in agreement with what we talked about, right? So just to fill this in, test 2, KP was 2, KI, KD is still 0, and now we have a peak time that went down just a little bit. We have overshoot that increased 48%, 40.4, and then we have C final moved up to 0.63, right? Okay, so just going back to the notes, this is as expected from the theory, right? So the theory said that we should get C final that starts to get higher, right? So if we increase the gain all the way up to infinity, this should eventually go to 1.5. Overshoot went up with the increase in KP, peak time went down, right? This is actually as expected, right? All right, we'll just increase the proportional gain one more time just to kind of prove a point. Make sure this trend still holds as we go up even more. Oops. Okay, and then we can plot this again. All right, and the trend just continues. So the overshoot didn't start move all that much on this one. Basically, it stayed the same, which is not quite as expected, but it's a physical system, doesn't obey theory perfectly. Peak time went down again. Overshoot was almost identical to where it was before. And then we have the C final is 0.8 something, 8.6. Okay, so largely following the trends. We also said that if we can continue to increase the proportional gain, and the C final should go up, but there are limits to this, right? So this is going to, if we are too aggressive with just the proportional gain, not adding any other terms, we have issues with overshoot, and we're going to eventually have issues with, it's not actually instability, it just really wild oscillations that don't die out. So just to elaborate the point, we're going to make the system not quite go unstable, but go to the brink of instability. So So I think sometimes students have a question like, okay, what does that instability actually mean? And I would just try and like think of this as actually an industrial robotic system and think about whether or not you would like this kind of behavior in your industrial robotic system. And it's going to actually kick out. It's going to, the safety overrides are going to kick in, and this is not going to continue to go on forever. But that's because we build in safety overrides in this system, okay, to protect it. So this is cranking up the gain to 11. Anyone ever seen Spinal Tap before? No? Okay. The joke's going to get worse and worse as I get older. So, you know, if your people are going to see Spinal Tap. Okay. All right. So then this is the response of the system. So this is oscillating pretty wildly. This actually didn't kick out. This usually kicks out. So let's crank the gain up even higher. So here it's actually, there you go. All right. So it just keeps on oscillating back and forth. All right. Oh, and then it died. Okay, so then the air kicked out. So it was basically dumping in too much energy that the system caught itself and knocked out. But you saw this performance here, which you can imagine if an industrial robotic system were to do that, you would step away, right? You would not want to be in the vicinity of that robot swinging around. But so I just wanted to kind of say this is it's actually pretty easy to make systems go unstable with proportional control or any type of control, right? And this is what it would kind of look like. This is actually going off in terms of going off as exponentials, but this is what we call marginally stable, but it just continues to oscillate without ever dying out. Okay. All right, this one we can't plot. We can't pull off overshoot on that. It's not going to work. So, okay. So next thing to test. Dial this back down. And so we saw that with a proportional gain of 3, we saw a pretty large overshoot, right? So 50% overshoot is usually deemed unacceptable. That would be really, really high with a controlled system. So we're just going to add just a little bit of the derivative term here. Roughly 10%, not quite. And run this again. That one. So we'll plot this so you can see a little bit better. Okay, so by adding just a little bit of that derivative term, remember going back to our notes from Monday that this provides virtual damping to the system. So I didn't mess with the bearings and throw sand in it and things to make the damping go up. I just by changing what's essentially operating GUI, which changes the line of code in my computer, I've added virtual damping. So with this test, this would be proportional gain of 3, PI 0, and 0.2. Peak time went down to 0.1. Overshoot went down to around 8%. And then C final, we said should not change. And we see it changed barely, right? So it's a physical system. It's not going to be perfect. It's not going to respond exactly the same way every time. But essentially, it didn't change at all, right? It went to the same C final position, right? And so in terms of like things that were inadequate in the system, we've cured a few of these, right? We cured the overshoot issue, but we also may care about the steady state value of this, right? So we can add integral control to the system. We can take a look at what that looks like. So I'm going to bring the derivative control down to 0. Integral up to 2. And then run this again. So this should still have quite a bit of overshoot associated with it. So I'll plot that so you can see it a little bit better in a second. Okay, so looking at what's going on, this isn't really tuned all that well, but a few things that we may notice. Unfortunately, this is going off the charts here, so this is only plotted for 6 seconds. As original overshoot, and then a pretty weak proportional integral term, but you can see that the position is actually reaching or going towards the intended value, right? So this is actually pulling off Cmax. The intended value is 1.5. This is pulling off a point farther than what this plot is showing, but then the Cmax value is, our C final is hitting 1.49. So right, it is converging to the final value, right? So we intended to go 1.5 radians. Over time, it is going to 1.5 radians, right? Overshoot is a little bit fictitious. We've added, by adding integral term, we've added both a pole and a zero, so it doesn't exactly match second order underdamped system, right? So we would not expect this rise to happen. The pure second order underdamped system, so it's starting to deviate from that behavior some, but this is still showing some of the benefits of